In example 2, we're asked to find another solution to a differential equation that once again has this structure where one or more of the coefficients on our y or y prime or y double prime terms include polynomials. So this 1 minus x squared, this x here, those prevent me from using standard chapter 3 techniques, and I'll instead have to use these series techniques. As with the previous example, I have a series solution that will be centered at x equals 0. So that means that my series will be written in terms of just x to the n. That allows me to assume that my solution has this form here, some unknown coefficient function times x to the nth power. Next, as we saw in the previous example, our goal will be to find the derivatives, the first derivative and second derivative of this assumed solution function. And these are in fact the exact same first and second derivatives that I calculated in the previous example. As a matter of fact, once you've worked through a couple of these problems on your own, you'll start to see and get a feel for like what these derivative and second derivative terms will look like. Anyways, let's go ahead and plug those in to my original differential equation. That gives me this equation here. And now I notice that on these first two series terms, I have coefficients outside the series. And so I will need to distribute those coefficients into the series. Let's think about how this is going to play out. If I distribute this 1 to this series, I just get 1 times the series. So the series won't change. Now when I distribute this negative x squared into this series, the x squared will be multiplied by all of the x terms in this series, and so the exponent on each x term will increase by 2 since it's being multiplied by this x squared. So I think I'll get these two series resulting from distributing the 1 and then the negative x squared through to this first series here. This negative could of course be written outside the series, in a sense factored outside all of the terms in the series, but I sort of prefer to have all of my series with a coefficient of just positive 1, so I choose to push that negative inside. Looking at this second term, I've got something similar going on. I'll push this negative x in. And notice that that increases the power on every one of the x terms by 1. Previously, the power on each x term was n minus 1. When I multiply by this additional x, that will increase that power. So now the power on each x term is just x to the n. And my last series here doesn't have any sort of coefficient term, so I can rewrite it in this line without any modification. My next step, as we saw in the previous example, is to somehow modify each of these series as necessary so that the power terms in every series agree. Looking across these 4 series, I noticed that 3 of them are already in the form x to the nth power. Exactly n. So I can use that x to the n as my target, and these 3 series won't need to be modified at all. This first series though is currently x to the n minus 2, and so I need to increase every n in this series expression by 2 so that this power term will also be x to the n. And now, as we've seen in several examples, I know that if I increase the n value within the statement of my series, that will force me to decrease the starting index by the corresponding amount. So I'm going to increase the n within this series expression so that I'll have x to the n, and increase by 2, and then that will require me to decrease this starting index by 2. And then, as I've already pointed out, these remaining series, these other 3 series, all have x to the n already. So I'll just copy those down, and I don't need to make any modifications to those series in this step. The other characteristic that I need to now address is the fact that these series now have different starting indices. And again, it feels a little strange to say, but it's like this third series has one less term than this fourth series, just as an example. They both have infinitely many terms, but since this one starts at n equals 0, feels like this has one fewer term. This second one starts at n equals 2, and so I need to, what I call, peel off any extra additional terms in series as necessary so that they will all have the same starting index. I can't decrease a starting index, so I effectively at this point have to look through and identify the highest starting index, which in this case is this n equal to 2. And then in all of my other series, I have to peel off any terms prior to the n equal 2 term. So once I'm done with this step, I'll have a few additional terms that are just by themselves, not part of the general series, plus this general series term, which will start at n equal to 2. So from this first series, I need to peel off two terms. I need to peel off the n equals 0 term and the n equals 1 term, so that the remaining terms will have this structure here where they start at n equal to 2. So I think if I peel off all of the terms prior to the n equals 2 term, I think these are what I get. So when n equals 0 and n equals 1 in this first series, I think I get these two terms here. In this third series, I just need to look at when n equals 1. That gives me this term here. And then in this last fourth series, I need the n equals 0 term and the n equals 1 term. That gives me these two terms here. Then, as I mentioned, since I've now got all of the series starting at n equals 2, I can collect all of the series expressions together and then factor out x sub n, so that my single general series expression will look like this. My next step is to set all of the coefficients equal, and there's actually kind of an extra detail here that we have to be careful of. If I look at these terms that I peeled off, for example, I notice that several of them are simply constants. These two terms here that I've highlighted are just constant. So the principle is that the constant term on the left must equal the coefficient on the constant term on the right. So what I'm going to do is I'm going to set those, the sum of those two terms, those constant terms, equal to 0 sort of separately. And then the other terms that I have up here up front are x to the first power terms, and the coefficients from those x to the first power terms need to be set equal to 0 separately. Next, I'll look at the terms in my series expression, and the coefficients on the general nth term needs to be 0 for every n, so I can take this entire coefficient expression and set it equal to 0. And now, in some ways, I'm basically done with the problem. As we've pointed out, our goal is to find a method or a formula or some algorithm by which I can compute all of the coefficients of my series, all of the coefficients of my solution. Between these three equations, I now have enough information to build all of those coefficients. I like to do just a little modification, a little bit of algebra to clean these up. So from this first equation, for example, I can deduce the relationship that a2 needs to be negative 1/2 times a sub 0. This second equation tells me that 6 times a3 equals 0, because the two a1 terms here cancel. So that tells me that a3 has to equal 0. And then in my third equation, this is really the main one that I focus on. First, I noticed that there are several a sub n terms. And when I look at the coefficient on all of those, I notice these n's will cancel. So this will simply be negative n squared plus 1. What I'd like to do is actually move that over to the right-hand side, and then I'll solve for a sub n plus 2. And then when I divide by these two linear factors to get a sub n plus 2 by itself, the n plus 1 will cancel if I were to factor this n squared minus 1. So I think my final recurrence relation is simply this here, that to get a coefficient, you take this fraction and you multiply the coefficient that was 2 steps prior to that. So collectively, these three equations determine my coefficients for the entire series. So in this context, I can stop there, and that is my answer. I'm usually kind of curious, and I'm interested in seeing how these coefficients play out. So I typically will spend just a brief moment writing out several of the coefficients. So I just spent a couple seconds here with a handheld calculator kind of working through some of these calculations, and I just want to stress that this is not really a required part of the problem. I'm simply exploring these coefficients to see if there's any particular pattern that I notice or any other properties that I can identify. But I don't want to invest too much time in this if it's not necessary. First thing I do notice is that since a sub 3 is 0, as was required by one of our equations, a sub 5 will be some coefficient times a sub 3. Therefore, it'll be some coefficient times 0, so a sub 5 will also be 0. And then for every odd index, all of the subsequent terms will continue to be 0 because we'll repeatedly multiply by this previous odd term. For my even terms, I wrote out several of the terms. It is true that all of my coefficients can be written in terms of a sub 0, but I'm not seeing a real clear pattern to these coefficients, and so I'm not going to spend a bunch of time trying to find some closed form expression for these coefficients. So as I said, I just worked through some computations quickly to see if there is a real clear pattern, and if there isn't, I'll just leave it as it is and move on. In example 3, we're presented once again with a differential equation which has some polynomial coefficients. This time we're also provided with initial conditions, so we'll have to see how we incorporate those into our final solution. So I've worked out some of the preliminary details here. First, note that we're told that the center of our series solution must be x equals 2. This implies that instead of simply having x to the n terms in the series, I'll now have x minus 2 to the n terms. Based on that detail, I've assumed my solution will have this structure here, and then as I work through the derivatives, fortunately, if you think about taking the derivative of a term of this form, you'll still simply have n times that term to the n minus 1. Technically, we need to apply the chain rule and multiply by the derivative of this inside component, but that derivative would just be 1. So when I look at y prime here, it feels very similar to the derivatives that I computed on previous examples. I have simply x minus 2 functioning as the variable instead. One other detail I want to point out quickly is that these initial conditions that are provided, notice that they occur at the x value of 2, and it is customary that those occur at the center of the series. And so if the center of the series is not explicitly stated, but we are provided with initial conditions, we can make the assumption that the series must be centered at the x value at which those initial conditions are provided. So as usual, I'll go ahead and plug in these series terms into my differential equation. And once I've plugged those coefficients into, or those series terms into the differential equation, my first step is to accommodate or distribute through any coefficients that exist on these series. In this first series, to distribute that 2 inside will be effortless. Actually, I don't even need to do it. I could just leave the 2 outside. When I look at the third series, the same is true. So the one that I really have to focus my attention on is this middle series. And the issue here is that if I was to try to push this x plus 1 into all of these series terms, there's sort of a mismatch. If I was to multiply x plus 1 times x minus 2, I get some complicated polynomial expression. I don't simply have x minus 2 anymore. And that's of course complicated by the fact that this x minus 2 is actually raised to a power. So to account for all of that, what I need to do is I need to force this coefficient to have the exact same structure as the power terms in my series. Well, that's a little weird because if it is x plus 1, I can't just make it be x plus 2. So the trick that I have to employ here is I have to add and subtract something so that this will have an x minus 2 component to it. Or maybe another way to think of it, as I've kind of done here, is I would need to take this x plus 1, I need to force it to have an x minus 2, Therefore, I need to have a plus 3 in here as well, so that this bracketed expression does equal the original coefficient that I had in parentheses here. So this is just a little step, a little trick to make sure that the coefficient is exactly the structure that will be compatible with the series terms. Now, as we've seen in previous examples, I'll distribute actually both of these through to the series. When I distribute this 3 through to the series, that doesn't affect the power terms at all. It just introduces an extra coefficient. When I distribute this x minus 2 through, each of these power terms will be multiplied by an additional x minus 2 term, so the exponent on those power terms will increase by 1. These first two series are unaffected. I guess I could have pushed those coefficients in. Maybe I'll do that in the next step. But the main term that I was focusing on here was this middle one. So let me go ahead and write the series that I'll get when I do the distribution that I just described. So as we see here, this one series kind of gave birth to these two separate series. The first one is the result of distributing this x minus 2 through. So you'll see that the power terms are now to one exponent higher, one integer value higher in the exponent. And then the second series, I just multiplied this 3 through, so I just incorporated that into these coefficient terms. But that 3 doesn't affect the power terms. All right, now I'm at the stage of incorporated all of the coefficients. So now I'm at the stage where I need to make all of my x minus 2 to a power terms agree. Right now I have a couple that are already x minus 2 to the n. So I simply need to work on this first one and this third one here. So modifying this first and third series as necessary leads this entire expression here. Now we're almost ready to factor out the x minus 2 and write this as a single series. But what I do note is that I have one series whose starting index is 1. The other 3 have starting indices at 0. That means that I'll have to peel off the n equals 0 term from each of these 3, the first, third, and fourth, so that all of the remaining series will have a starting index of 1. So if I compute the n equals 0 terms from this first series, from this third series, and from this fourth series, I believe that these are the terms that I get. I do notice one little typo there. This should just be a sub 1. And if I peel those terms off, then all of this series can be written in terms of one combined series that starts at n equals 1. And in this combined series, I will factor out the x minus 2 to the nth term, so that in the brackets here I will have isolated the entire general coefficient term. And now I'm ready to set all of the coefficients equal to 0, and that will hopefully give me an algorithm or a formula by which I can recursively define all of the coefficients of this series. So here I've set this coefficient expression equal to 0. I did in fact sort of group these a sub n terms because those are like terms. Now let me solve this. What I typically do is I solve this equation for the highest term. In this case, that would be this n plus 2 term. So I have a recursive formula that will allow me to compute the next coefficient based on the previous coefficient and the coefficient 2 prior to the one that I'm interested in. And of course there's these expressions here that modify those previous coefficients and come together to determine what the next coefficient will be. So collectively, these two equations determine all of the coefficients of my series. So I think of these as being the answer to this problem. In this particular problem, I do have initial conditions that I need to incorporate. So I want to go ahead and work through a couple more steps to provide a little bit more detail to demonstrate how those initial conditions get incorporated into my solution. First, let me just make a general comment or observation about the structure of my solution. Remember that y is a series expanded about x equals 2. So if I don't try to give any specific detail regarding these coefficients, if I simply just write them as a sub 0, a sub 1, etc., then this is the general structure of my solution. Well, one thing I note is that since every one of these terms has an x minus 2 in it, then if I plug in x equals 2, all of those terms cancel out. That term will go to 0, that term will go to 0. That's true for every term in my series except for the first constant term, a sub 0. So if I was to plug x equals 2 into this entire series, all of the terms would vanish except for a sub 0. Well, plugging in x equals 2 is exactly the initial condition that I was given. So if I look back at the statement of the problem and I can identify which value was given as y of 0, that is exactly my a sub 0 value. Something similar happens if I take the first derivative. If I differentiate a sub 0, that is just a constant, so that goes to 0. If I differentiate this linear term, the derivative will simply be a sub 1. If I differentiate this quadratic term, I'll bring the power down, then I'll have x minus 2 to the first power, etc. And once again, if I plug, I do have one typo. Once again, if I plug 2 into this derivative expression, then every single term will go to 0 except for what's now my constant, which in this case is a sub 0. I think I said that incorrectly. I think I said a sub 0, but the constant is now a sub 1. And I noticed another mistake that I've made here. I'm talking about plugging in x equals 2, and so the initial condition that we were given was y of 2, and that will turn out to be my a sub 0 value. So I just wanted to demonstrate that these initial conditions, y of 2 and y prime of 2, will actually correspond directly to the values of a sub 0 and a sub 1, those first two coefficients in my series. And this is due to the fact that the center of my series is 2. So plugging in those values allows me to directly identify these first two coefficients. So based on these ideas, if I scroll back up and look at the given initial conditions, we were told that y of 2 would equal 1 and y prime of 2 would equal negative 1. Therefore, I can conclude that those are my first two coefficients. So in some sense, now we have all of the ingredients necessary to compute all of the coefficients of our series. So on the one hand, it feels like we have completed the problem. We can go ahead and do some additional computations to identify the first several coefficients of the series, and then we'll write out the first several actual terms of this series. So I have the first two coefficients based on those initial conditions, and now I have this formula I just copied and pasted from above that allows me to define the next coefficient in terms of the previous two coefficients. So for example, if I want a sub 2, then in this formula, n will equal 0. So then evaluating this right-hand side, I'll have negative 3 halves, 1 over 2 times 1 times a sub 1. So that's what I have in this first term here. And then in this second fraction, again, I'm plugging in n equals 0. So that gives me 3 over 2 times 1 times a sub 0. Now a sub 1 and a sub 0 are specific terms that I have previously identified. So I can plug those values in. And it looks like a sub 2 actually simplifies to 0. To find a sub 3, I will once again utilize this formula, plugging in n equal to 1, so that I'll have a sub 3. And the formula will yield an expression for a sub 3 in terms of the two previous terms, a sub 2 and a sub 0. We have already identified what those values are. Plugging in what I know for a sub 2 and a sub 1, simplifying, it appears that I get a value of 1/3. Let me continue this process and just kind of work through a few more computations. So doing a few more computations, I've been able to calculate few more coefficients up to like the 6th coefficient. I guess technically the 7th coefficient because we have a sub 0 as well. And I admit that these computations are a little tedious. I've got my handheld calculator here trying to figure out these fractions and stuff, but you can imagine writing a program that could calculate these coefficients for you very efficiently, and so you could potentially generate hundreds of coefficients in just a matter of seconds. Let me go ahead as a last step here and just take these coefficients and put them onto the power terms, onto the x terms as appropriate, just to get a quick glimpse of the first several terms in my actual series solution. So using the coefficients I've computed and putting them on the appropriate terms, I get a polynomial approximation for my solution up to the 6th term that looks something like this. As I mentioned, this is of course not the perfect actual analytic solution because that would require me to write out infinitely many terms, but there are lots of contexts where even with a small number of terms, such as I was able to compute by hand here in this example, I would be able to attain an appropriate or desired level of accuracy for whatever problem I'm trying to solve. So that wraps up section 6.3. We have demonstrated how we can use series to solve differential equations that we wouldn't be able to solve using any other techniques that we've covered so far this semester.